Hello. As we start Unit 4, the first several days are going to be revolving around graphing and how graphing relates to derivatives and second derivatives. So the first definition we have here is of a critical point. And a critical point is where the derivative, or f prime, is 0 or undefined. So slope-wise, that's going to be where the slope is 0 or has a horizontal tangent line, or undefined, which means it has a vertical tangent line. These next four terms are pretty straightforward: local max, local min, absolute max, absolute min. A maximum is going to occur if at f of p, if f of p is greater than or equal to f of x near where p is. So if it's the biggest guy in its local neighborhood, so if this was my graph, that would be a local maximum. Local min, similar definition, just less than. So similar graph. This would be a local minimum, but there's more values less than it on the graph. Absolute is what it sounds like. It's going to be the biggest for all x. So I'm going to pause and write those definitions down. So here's those definitions if you want to pause and write them down. So f of r, if f of r is bigger than f of x for all in the domain. But again, it's exactly what it sounds like. If it's the biggest value on the entire graph. Same with a minimum. Okay, if there's no values lower than it, then it's an absolute minimum. The first derivative test is a very important one. So there's two conditions that need to be met to use this. First is the function must be continuous at whatever value we are investigating. So if it's continuous at c, and c is going to be our value we're interested in, and c is a critical point, so if c is continuous and c is a critical point, so the derivative is either 0 or undefined, there's two cases. If f prime of x, so if the derivative switches from positive to negative. Okay, so picture a graph, and I'm going to point to this one. If it goes up and then back down, that means that there is a maximum at that spot. Typically, we'll just call it a local maximum because we don't have more information, but it could also be absolute. But what we know is it is a maximum if it goes from increasing to decreasing, and c is a critical point. On the flip side of that, if f of x, f prime switches from negative to positive, c is a minimum. So just to illustrate, if it goes up and then back down, our value is a maximum. If it goes decreasing to increasing, then our graph is a minimum with an M. So we're going to have a bunch of graphs here, and we're going to analyze them using what we're going to call an f prime chart. So I'm going to make a number line going to label this number line f prime of x. And that's a good habit to get into because we're going to have lines for f prime, for f double prime. So understanding what's labeled on that number line is important. Now I'm going to identify all the critical points or other things that we need to be interested in. So my first critical point is going to be at 1. And I'm just going to put it infinity here because this is going to be an asymptote. At 2, I'm going to put an x there because that's not differentiable because there's no value there. At 3, I'm going to put an x because it's not differentiable there either. At 4, we have a corner, so it's not differentiable there. It is, however, continuous. So for the number line chart, what we're going to do is show what's happening with the derivative. So the derivative, if the function is increasing, then the derivative is positive. If the function is decreasing, then our derivative is negative. Still decreasing. From 3 to 4, it is increasing. And from 4 to 5, our graph is decreasing. Now, in this graph, so now what I'm going to do is, so this graph is going up, it's going down, it's going down, it's going up, and it's going down. Okay, so from the graph, we can tell that we have a minimum here and we have a maximum here. From the number line chart, it may look like we have a maximum here, but this is discontinuous here. However, at 3 and 4, even though it's not differentiable there, the derivative is undefined, it is continuous. So this is a minimum, and this one is a maximum. Now I'm going to go into more detail. So for B here, we have this parabola. So my number line chart, we labeled the critical point. There is only one. There's only one location here at 3 where our derivative is 0. So I'm going to go ahead and label 0 there. Okay. Leading up to 3, my derivative is going to be negative because my graph is decreasing. Past that point, it's going to be increasing. So now, if I didn't have the graph and all I had was this information here, I know that my graph is decreasing here, it's increasing here. So it's increasing when x is less than, when x is greater than 3. It's decreasing when x is less than 3. And oftentimes you're going to be asked to justify. So my justification would be it's increasing because f prime of x is greater than 0. Here it's decreasing because f prime of x is less than 0. So if you are asked to justify, that's what you would need to say. It is increasing at some range because the derivative is positive. It's decreasing because the derivative is negative. The other thing we can tell, again, we can tell all of this just from this number line, is that 3 is a minimum and our justification would be because f prime of x switches from negative to positive. That would be our justification from the first derivative test. F of x, or sorry, x equals 3 is a minimum because f prime switches from negative to positive. You have to be very specific here. If you just say it's a minimum because it switches from negative to positive, that's not specific enough. It has to be f prime switches from negative to positive. Okay, so here's another one we're going to take the information from the graph and put it on a number line. Label it f prime. And my only critical point, the only point I'm going to put on the number line, is -1. And our derivative there is 0. So label that 0. This one is increasing, so the derivative would be positive. Then it's decreasing, so now it's negative. So this graph goes up, then down. So from the number line, we know this is a maximum. So again, I can tell all of that just from that number line. I don't need the graph, and that's what we're working towards. So I can say that this graph is increasing when x is less than -1, and I know that because f prime of x is greater than 0. I know this graph is decreasing from our number line when x is greater than -1, because f prime of x is less than 0. And I know that x equals -1 is a maximum. And my justification, because f prime of x switches from positive to negative. So if you ever have to justify either increasing or decreasing, or whether a point is a maximum or a minimum, those are the qualifications you're going to do. For the rest of the graphs, I'm not going to do the justifications. We're just going to talk about the relationship between the number line and the graph and what we can tell. So here my number line would contain 2 critical points at -2 and 2. The slope would be 0 at both of those. This one goes from increasing to decreasing to increasing. So if this is all I had, again, I didn't have the graph, but I know that my graph is going up, then my graph is going down, then my graph is going up, which means we have a maximum here and we have a minimum here. So I'm just going to label that. We have a max at x equals -2. We have a minimum at x equals 2, and then if asked to justify, you would justify it like we did in the previous 2 examples. Okay, looking at this one, how many critical points do we have? So our critical points are going to be at -1, 0, and 1. Our derivative, our slope at all of those points is 0. This graph is decreasing, then it's increasing, then it's decreasing, then it's increasing. So numerically, the derivative would be negative, positive, negative, then positive. So then we know it's decreasing, then it's increasing, then it's decreasing, then it's increasing. So we have a minimum here, a maximum here, a minimum here. So we have 2 minimums at x equals -1 and x equals 1, and we have a maximum at x equals 0. This next one, we know, we're looking at this graph, we can tell that there is no maximums or minimums. So how do we tell that on the number line? So let's take this graph and put it on the number line. The only place where the derivative is undefined is at 0. And I'm going to put an infinity there because there's an asymptote there. So this graph goes from positive to negative. So it's increasing, then it's decreasing. But unlike the previous examples, this isn't continuous here. So if I'm looking at this number line, this being discontinuous here tells me that there is no max or no min. Okay, specifically a minimum in this, or maximum in this case, because it's increasing and decreasing. So does it have a maximum? No. So you can have this going from positive to negative without there being a maximum. Okay, so we're going to put this next one on the number line. So the derivative is undefined at -1 because there's an asymptote there. There's a slope of 0 there at 0. So this would go from, this one is decreasing, then it's decreasing, then it's increasing. So I should just make those green, huh? So this one is just an asymptote. This one is a minimum for this graph. Now we're going to talk about concavity. So concavity is kind of the shape of the graph. So if a graph is concave down, okay, our graph is going to look something like that. Okay, it means that the slopes are decreasing. So if I use this, my slopes would be positive, then they're 0, then they're negative. So the slopes themselves are decreasing. It means f prime of x is decreasing. And that's just saying the same thing. Slopes and f prime are the same, which means f double prime, the derivative of this, if this is decreasing, then its derivative is negative. So we make a sad face for concave down. Concave up is going to look like that. Okay, where my slopes were negative, then they're 0, then they're positive. And they don't have to go from negative to positive. And you'll see some examples here. So here the slopes are increasing. Which means f prime is increasing. Which means f double prime, if this is increasing, its derivative is positive. So we'll say positive for concave up. An inflection point is a point on the graph that has a tangent line and the concavity changes. So now we're going to make a second derivative chart. And again, we're going to go from the graph to the chart in the eventual goal of you'd be able to go from the chart to the graph. So this one, something going on at 1, something going on at 2, 3, and 4. Okay, so at 1, we still have that asymptote. 2, my function is undefined, which means the first derivative is undefined, which means the second derivative is undefined. At 3, there's a cusp, so there was no second derivative. If there was no first derivative, which means there's no second derivative. And same at 4, we have a corner, which meant there was no derivative, which means there's no second derivative. Now we're going to label this with concavity. So this part of the graph is concave up, so the second derivative would be positive. This too is concave up. Then it switches here. This is concave down. This is concave down. This, if I take the derivative of this, it would be a constant. So the second derivative would be 0, which means there is no concavity, which from the graph, it's just a straight line. So there's no concavity to it. So this would be concave up, concave up, concave down, and a constant. But there's no inflection points because at the place where it switches concavity, there's no tangent line there because it's undefined. So there is no inflection point here. So let's look at a simpler, couple simple examples. Okay, so we have a parabola, and we're going to create a chart for the second derivative. Okay, so this one, the derivative of the derivative, so we're just looking at the concavity, this one is always concave up, which means the second derivative would always be positive. So we'd say this is concave up because f double prime of x is greater than 0. So if you were asked to justify concavity, that will always come from the second derivative and whether it is positive or negative. Here, from the graph, this is slightly concave up to about here, then it's concave down to about here, then it has a slight increase again. Okay, so this one at -3, my second derivative would be 0. Here, my second derivative at 3 would be 0. And then this one is concave up, then it's concave down, then it's concave up. So we would be able to say that this is, if I just had this information, we know it was concave up, concave down, concave up at those points. So information we can tell from the number line. We can tell that this graph is concave up when x is less than -3, when x is greater than 3, because f double prime of x is greater than 0. This graph is concave down between -3 and 3, because f double prime of x is less than 0. Okay, and on this graph, at -3 and at 3, the graph switches concavity. It goes concave up to concave down to concave up. So x equals -3 and x equals 3 are inflection points. Okay, and we can call them inflection points or points of inflection. That is interchangeable. And how do we justify that? Because the concavity switches. So because f double prime of x switches sign. So if you're ever asked to justify why something is an inflection point, it's because the f double prime switches from positive to negative or negative to positive, but all you have to say is that it switches. So just go through these quickly. So for this one, it's concave up to here, and then it's concave down. So this one would be concave up, concave down, which means that 1 is an inflection point. I'm just going to abbreviate IP for now. For this one, at, what's that, about -1/2, this graph is concave up, but at -1/2, we have an asymptote. This would be concave down, but because there's no tangent line at -1/2, this is not an inflection point. So there is no inflection point, even though it switches concavity. The second derivative test is another way to prove whether a point is a maximum or a minimum. So the second derivative test says if you have a twice differentiable function at x0, and x0 is a critical value. So if the first derivative is 0, and that's really important, if the second derivative is greater than 0, that means our graph is concave up. Well, if it's concave up and our slope is 0, that means we have a minimum. If the first derivative is 0 and the graph at that point is concave down, meaning the second derivative is less than 0, then we have a maximum. But if both the first derivative and the second derivative are 0, we can't test. We can't do anything. Test fails and there's no conclusion. Okay, so let's go through, without the graph, how can we tell different things? So we've got x to the 4th minus 2x squared. So the derivative is going to be 4x cubed minus 4x. Okay, the critical values are the values where it is equal to 0. So 0 equals 4x cubed minus 4x. So 0 equals, I'll factor out a 4x, which leaves me with x squared minus 1. So this is going to be x minus 1, x plus 1. So the critical points are the values that make the derivative 0, which is going to be x equals 0, 1, and -1 are all the critical values. Okay, what is the second derivative? The second derivative is going to be 12x squared minus 4. The values that satisfy the hypothesis of the second derivative test. So we have a twice differentiable function, and all 3 of these are critical values. So 0, 1, and -1 are all values that satisfy the hypothesis. So we can use the second derivative test without a graph to determine if these are minimums or are they maximums, or do we not have enough information. So we're going to use the second derivative and evaluate it at 0, evaluate it at 1, and evaluate it at -1. So the second derivative at 0, if I plug a 0 in, is going to be -4. The second derivative at 1, we're going to have 12 minus 4, which is 8. If I evaluate the second derivative at -1, we will also get 8. So we know the first derivative is 0 for all 3 of these. For 0, the second derivative was negative. So that means that at that point, the graph was concave down and has a derivative of 0. So when x equals 0, we have a maximum. So to justify this, you would say because f prime of 0 was 0 and the second derivative was less than 0, which means it was concave down, which means we have a maximum. The other two were both positive second derivative which makes them minimums. Okay, because if it's concave up, okay, and you can picture that concave up, that means and the slope was 0, that means they're at the bottom of that curve. Because f prime of, I'll just say f prime equals 0, and the second derivative was greater than 0. Okay, so this is going to be like that other example. So first we're going to take the derivative of sine squared x. So that's going to be 2 sine x times the derivative of sine x, which is cosine of x. So the critical values are going to be when that equals 0, which is either where sine equals 0 or where cosine equals 0. Now there's an infinite number of places that's true, but we want the one specifically between 0 and pi. So between 0 and pi, inclusive, sine is 0 at 0 and at pi. Cosine is 0 up at the top of the circle at pi over 2. Okay, the second derivative we're going to find using the product rule. So we're going to have 2, derivative of sine is cosine, times cosine, plus derivative of cosine is a negative sine, times the 2 sine. So this is going to be 2 cosine squared x minus 2 sine squared x. The values that satisfy the hypothesis are all three of these. Okay, 0, pi over 2, and pi are all second. We can take two derivatives. We took two derivatives, and their first derivative value is 0. Now we're going to plug them in to determine whether they are maximums or minimums. So the second derivative of 0, if I plug 0 in here, cosine of 0 is 1. So we're going to have 2 minus sine of 0 is 0. So that's going to be 2. The second derivative of pi over 2, derivative of pi over 2 is, cosine of pi over 2 is 0. Sine of pi over 2 is 1. So we're going to have a negative 2. And at pi, cosine is negative 1, but we're squaring it. And then sine is 0. So our second derivative will be positive 2. Okay, so what does that tell us? Our first derivative is 0 at all three of these locations. For 0 and pi, the graph is concave up, which means these are minimums. At pi over 2, my derivative is negative, so this is a maximum. And again, you would justify it the same way that we did on the previous example, saying the first derivative is 0 and the second derivative is either positive for minimums or negative for maximums. Okay, for this example, we're going to do a full number line analysis of x to the fourth minus 4x cubed plus 2 in order to graph it. So we're going to find the critical points for f of x and the critical points for f prime. So we'll take the first derivative, okay, and figure out where it equals 0. So go ahead and factor out a 4x squared, which leaves me with an x minus 3. So my critical points here are 0 and 3. The critical points for the second derivative, or for the first derivative, we'll take the second derivative. So the derivative of this is going to be 12x squared minus 24x. Set that equal to 0, so we can factor out a 12x, which leaves me with x minus 2. So my critical points here are 0 and 2. Now, determine where the function is increasing and decreasing. So we're going to go to the first derivative. So this is my first derivative. I'm actually going to use this factored version to come up with what's happening. So make a number line for each factor, which in this case there's just these two. This one is 0 at 0. This one is 0 when x is 3. Besides 0, 4x squared is always going to be positive. Okay, this one, if I plug in a number less than 3, like 0, we're going to get a negative value. If I plug in a number bigger, we're going to get a positive value. So now I can determine whether f prime is positive or negative at different locations. It is 0 at both 0 and 3, and we are multiplying these two factors together. So for this area, we're multiplying a positive times a negative, which gives me a negative. Here I'm multiplying a positive times a negative, so that's a negative, and here I'm multiplying a positive times a positive, which makes this positive. So now, without ever looking at the graph, I can tell where f is increasing and decreasing. So f is increasing when x is greater than 3. It is decreasing when x is less than 0 and between 0 and 3. At 0, it's doing neither. Okay, name the extrema. Okay, so this graph was going down, then going up. So right here, I have a minimum. So x equals 3 is a minimum. And we want to justify our answer. So we justify it because f prime of x switches from negative to positive. That's all I have to say to justify it. To determine where the graph is concave up and concave down, we're going to use our second derivative here. And again, I'm going to use the factored version here. So I'm going to have a number line for 12x. I'm going to have a number line for x minus 2. And then I'm going to have a third number line for the second derivative, based on what we get on the first two number lines. So here, this is going to be 0 at 0. Here, this is going to be 0 at 2. So there's two critical points on this line. This should be 2 and 0 on top. All right, so we got a little space here, but this one is going to be negative going to positive. This one is going to be negative going to positive. And if you're unsure, you can pick a test point. But these, if you were to graph them, are just lines that are increasing. So the second derivative, we have a negative times a negative, which makes this concave up. The second derivative here is 0 at those two. A positive times a negative is negative. A positive times a positive is positive. So where do we have any inflection points? Any place where the concavity switches, which is going to be at x equals 0 and x equals 2. Justify our answer because f double prime switches sign. So now we're going to take that information from the previous page to graph f of x. So these are just the number lines that I copied over. So we've already made these determinations. So this graph is decreasing, then it's decreasing, then it's increasing. So we have a minimum. The graph is concave up, then it's concave down, then it's concave up. And we have an inflection point at both 0 and 2. So the 3 points that we care most about are 0, 2, and 3. So if I evaluate those in the function, and you can just plug these in the interest of time, I'm just going to give them to you. So f of 0 is 2, f of 2 is negative 14, and f of 3 is negative 25. So for my graph, we're going to favor the negative side. Okay, and we care about 0, 2, and 3. So I'm going to call that 2. We'll just pretend that's negative 14 and negative 25. You can get more accurate if you want to. So my 3 known points, I know 0 is 2, f of 2 is negative 14, and f of 3 is negative 25. So my graph at 2 is decreasing but concave up. It switches concavity at 2 to concave down, and it's decreasing to 2, which is an inflection point. So it's going to switch concavity, but still decreasing. Then at 3, it's a minimum, and it goes from decreasing to increasing. So now we're going to graph just from the number line. Now we have no function values, so that makes it a little bit tricky, and it makes it that there's more than one possible answer. But looking at this number line, for f prime, my graph is decreasing, increasing, increasing, then decreasing, which means we have a minimum here, a plateau here, because it goes increasing, then 0, then increasing, and then we have a maximum. From the second derivative, we have a concave up, a concave down, a concave up, and a concave down. So we're going to have an inflection point at all of those locations where it switches concavity. So we're going to draw a graph here, and again, there's more than one correct way to draw this. Okay, so my points that I care about, at negative 3 we have a minimum. At negative 1 we have a plateau, and at 3 we have a maximum. So I'm just going to put a point way down here for the minimum, and I'm going to put a point way up here for the maximum. And then we're going to use these both lines to shape this. So going to negative 3, we are decreasing but concave up. Then we're increasing to negative 2, where our graph switches concavity, but it's still increasing all the way to negative 1, where it has a plateau. It's still increasing, but now it switches to concave up all the way to 2, where it switches concavity and is then concave down, and then it goes down. Okay, so we'll do this one quickly. So this one is decreasing, then it's increasing. We have an asymptote, then it's increasing, then it's decreasing. So we have a minimum here, we have a maximum here. This one is concave up and concave down. And really this is going to kind of show us what this graph looks like. So at 3, we have an asymptote. At 2, we have a minimum. but it's always concave up there. At 4, we have a maximum, and it's always concave down. Again, your graph can look very, very different than that as long as we have a minimum, a maximum, concave up, and concave down. Okay, so one final example here. So where does this have a relative minimum? So we're going to take the derivative, 24x to the 5th minus 24x squared plus 0. I want to know where that equals 0. So I'll factor out my biggest common factor, which is 24x squared, which leaves me with x cubed minus 1. So I'm going to make a number line for each of those. Okay, so this one's always going to be positive except for at 0, it's 0. This one has a critical point at 1, where it's going to be 0. This is always positive. This one's going to be negative until it gets to 1, and then it's going to be positive. And if you picture the graph of a cubic function, that's what it's going to do. So my derivative is going to be negative 0, negative 0, positive. So we have down, down, up. So 1 is our only local minimum. So thank you. That was a long video, and we're going to continue graphing over the next couple of days.